Now we're going to talk about the relationship between pointers and arrays. But before we do that, let's update our understanding of how the increment and decrement operators work. So, as I mentioned in a previous video, the increment operator adds 1 to a variable and the decrement operator subtracts 1 from a variable. And we also saw that there's two different versions of these. The prefix version has the symbols written before the variable name, and the postfix version puts the symbols after the variable name. Now, does it matter which of those two you use? Well, it turns out the answer is it depends. So why am I talking about this now? Well, some people, when they write their code using pointers, choose to use these operators. And in many cases, whether or not you choose the prefix or the postfix version will affect how the code works when you're using those pointers. So we need a better understanding of what we can do and how things work. So let's look at these two lines right here. Each statement only does one thing: add 1 to x. And it doesn't matter then whether or not I put the plus plus after x, which is the postfix version, or I put the plus plus before x, which is the prefix version. There's no ambiguity here about what to do. It's simply add 1 to x. But now when I get to these two statements, I'm really saying to do two different things. In some order, I'm saying add y to 3 and assign that to x, but also increment y by 1. So now whether or not I use the postfix version or the prefix version of the increment operator changes what the ultimate value in x will be. This version, because it uses the postfix version, which means the pluses come after the y, says when you get to this point, use the current value of y to add to 3, and then afterwards increment y by 1. In the prefix version, in which the symbols come before the y, it says increment before you use y, and then take that value and add it to 3. So this single statement here is equivalent to these two statements. Add the current value of y to 3, assign that to x, and then increment y by 1. These two sides are the same. This says increment y first by 1, and now take the new value of y and add it to 3 to get x. On occasions, I may write something like this or this, but in most cases, I prefer to do separate statements. And the reason for that is just that I have to concentrate more to make sure I don't make a mistake when trying to use one of these. That is, maybe I wrote this when I should have written this. So I believe that if I do two separate statements, there's less likelihood that I'll make a mistake. And one day I may be tired when I'm writing code, and that's when bugs like these start to slip in. So I just prefer to do this, but ultimately they achieve the same results. Here's some code to demonstrate that. So down here, I want to add 3 to the value of b and also increment b at some point. And here I want to add 3 to d and also increment d at some point. So b and d both start off with a value of 5. Right here I'm using the postfix operator, so this says increment b after it's used. So when I first get here, b is 5, so I have 3 plus 5 is 8. I assign that to a, then add 1 to b to get 6. And we can see that's what I have here when I print using this line. On this line, it says increment d first to make d equal 6, and now 3 plus 6 is equal to 9, and that's the value of c, even though d and b have the same values. So I mentioned on an earlier slide that some people like to use the increment or decrement operators with pointers. So what does it mean to do that? Here I've created a double with an initial value of 99. I create a pointer to a double. And now when I print the address of num, we can see it ends with 3b00. I wrote pointer plus plus, so I'm incrementing by 1, we think. And now when I print the contents of pointer, it says 3b08. So what happened here? Why is it not 3b01? Well, it turns out that when I use the increment and decrement operators, or actually use other ways of incrementing or decrementing pointers is technically the more accurate way of saying it, I'm not actually using traditional arithmetic. So before we see what I'm actually doing, which is called pointer arithmetic, but before we discuss how it works, let me make clear that this isn't because I'm using plus plus as opposed to one of these two statements. All three of these would have achieved this same result here. And just like with other types of statements, I do have the flexibility of saying something like pointer equals pointer plus 5 if I want to, or pointer plus equal 5. None of those work in the traditional sense. All of those are really using what's called pointer arithmetic. So what pointer arithmetic does is it updates the address by the amount of the size of the object you're pointing at. That is, it moves to the next object if I say increment by 1. And if I were to say increment by z, that means it's going to update the addressing by the size of z times the size of an object. Let's see a picture that hopefully make more sense. So let's say I have a street here. And on this street we have these houses. And on this street, a lot is 40 foot wide. And I have another street. And on this lot, or excuse me, on this street, the lots are bigger. So here's a house, here's a house, here's a house, here's a house, and so forth. But these lots are 80 feet wide. So if I'm at house X, and I say I want you to go 3 houses away from here, you go 1 house, 2 house, 3 houses. I'd be right here at house Y, right? But in terms of distance, which is what's important if I really have to walk it, how far did I go? Well, going from here to here was 40 feet. And from here to here was 40 feet. From here to here was 40 feet. So I really went at whatever the location of X is, and I added to that 3 times 40 feet equals 140 feet of distance. Down here, let's say I'm at house A, and I say I want you to go 3 houses away. So you go from here to here, here to here, here to here, to house B. Now how far did I go? Well, from A to this point is 80 feet. From here to this point is 80 feet. From here to B is 80 feet. So here I went 3 times 80 feet, which is 240 feet of distance. At an abstract level, I really did the same thing in both cases. I went 3 houses away. But in terms of actual distance, I didn't do the same thing. Here I went 120 feet, and here I went 240 feet. So what does that have to do with anything? Well, in my computer, if I have an int, and on modern computers, I've told you that's equal to 4 bytes of spacing. Let's say an int takes up these 4 bytes. And so this first address, we'll say that's BF00. And that's address BF01. That's address BF02. Sorry, BF02. That's BF03. And then if I were to store another int next to that, where's it at? BF04. So if I'm pointing, so if my pointer, let's write it this way, is equal to address BF00, and I do pointer plus plus, I want to point at the next int, which means now I'm adding 4 bytes worth of addressing. And if we had another int here, this would be what? This would be BF08. Because this is 4, 5, 6, and 7. So that means if I, instead of doing this, I wrote pointer plus equal to, what it's really doing is taking BF00 plus size of an int times 2 to get BF08. So this address here, which is stored in pointer, it says 2 times 4 is equal to 8. BF00 plus 8 is BF08. And if I was pointing at doubles, which are really 8 bytes, that means pointer plus plus would increment by 8. And pointer plus equal 2 would increment by 2 times 8, which is 16. That's how the pointer arithmetic works. But the computer is taking care of all that for me. I don't have to worry about it in the vast majority of cases. So I said earlier that we can use increment and decrement operators with pointers, but it turns out that we also, in the same statement, can use the dereference operator with a pointer variable. So the same pointer variable can have a dereference operator applied to it, as well as an increment or decrement operator applied to it, which leads to some very challenging things if you're trying to keep track of what's going on. Not the least of which is this. The postfix versions of the increment and decrement operators have higher precedence than the dereference operator, and they're also evaluated left to right. But the prefix versions of the increment and decrement operators are not only at the same level as the star, but they're evaluated right to left. All right, so what are our possibilities? Well, it turns out, assuming pointer is pointing at the right type of thing, this statement and this statement and this statement and this statement are all legal, but they all technically do something different. So these two right here increment the value that's being pointed at. Let's say pointer is a pointer to an int, and that int has a value of 7. So here, because I'm using the prefix version, and these are evaluated right to left, right? It says I want to do the incrementing before I use the value. So this takes, if I'm pointing at the number 7, this says I want to increment the 7 to 8 and then use it. This one, and here I need the parentheses to distinguish between this and this. All right. This one says use the current value of 7 and then increment that 7 to 8 after I've used it. These two versions increment the address that's being pointed at and then use the value being pointed at. This one does it before I use the value, and this does it afterwards. So if, for example, this was pointing to an element of an array, I might use the current value in the array and then move the pointer or change its value such that it pointed at the next element of the array. This one says go ahead and point to the next element in the array, then use that value. I hardly ever use any of these because it's really difficult for me to understand what's happening when I'm looking at them. So each of these can be replaced by multiple statements, and that's really my preference. There's very few situations where I would want to do this. I'd rather just use the separate statements and not have to think as hard about whether or not I'm doing the right thing. So why even learn these? Well, some people do use these. And so we haven't talked about strings yet, but there is a string library in C. And if you ever look at somebody's implementation of the string library functions, you'll see it's very common for them to use pointers and to use statements like one of these within that code. So if you don't know they exist and sort of how they work, you really don't have any idea of how that code is working. So that's why I think you still need to know it. So pointers and arrays are actually closely linked in C. Now many people, probably the majority of people, will tell you arrays are really just pointers. And strictly speaking, that's not true. There are situations in which they can be used equivalently in terms of the code, but there's also situations where they can't. And even then, conceptually, I don't consider them the same, because a pointer is a variable that stores the address of something else, while an array is really what we call a data structure. This data structure here holds this data. And it imposes a certain type of structure to it. I know that sounds redundant when I said data structure, but if you go on to take a data structures course, you'll see there's actually lots of ways to structure data for various reasons. So each data structure has its pros and cons, and that's why you learn a variety of those. So they're not technically the same. But when I do write the name of an array, like I did here, not here, but here where I'm using as on the right hand side of an equal sign, well then what it evaluates to is the first element of the array. I cannot stress this enough to you. I didn't say it points to the 5, although in this case it does. If I ask you what is stored in data here, it's an array of ints. Therefore, writing data gives me the address of an int. But if this had been a two-dimensional array of ints, just writing data would have given me the address of a row in that array. All right, so those aren't technically the same at some level. It would still be the same number. It still would be a 5 if that's what that first row contained at the beginning. But in terms of the pointers, they're not the same. So since data gives me the address of the first element of the array, and the first element is an int, then data pointer is of type pointer to int. So int star data pointer equals data gives me the address of the 5. But equivalently in this case, I could have said data 0, which gives me the 5, and then say, using the address operator, what is the address of that element of the 5 in this case? And that's also a pointer to an int. So each of these do the same thing. And in fact, when I dereference data pointer or first pointer, as I do here, you can see they both just give me the 5. And if I were to increment either of these by 1, they would both increment to the 6. So those two pointers are the same. They both point to an int. Up till now, when I wanted to work with an array, I use what we call subscript notation. Okay, that is, I provide the subscript of this array or the element within the array that I want to work with. So if I want the address of each element, I can use ampersand data sub I. And if I want the value at that address, I can just use data sub I. So you can see when I did that, I get these addresses 7190, 7194, because these are ints, 7198, and they contain these values 5, 6, and 7. But they're all alternatives to subscript notation. I also can use pointer notation. So look at what I did here. I said data plus I to get the address, and these are the same addresses that I had on the previous slide. And I can write data plus I and then dereference that to get those values. And of course, these are the same values. So how does this work? Well, let's also point out while we're here that I don't technically need these parentheses. I just do that for consistency. But what it's doing is, when I is equal to 0, this is, okay, take the address of data, or stored in data, which is the address of 5, add 0 times the size of an int to that, so data plus 0 is still data, and it gives me that address. This says data plus 0 is data, which is the address of the 5, and then I dereference it to get what's at that address. Then I increment I by 1, so now I will be 1. But remember, because of pointer arithmetic, when I write data plus 1, it's really data plus 1 times the size of an int, so it's data plus 4 technically. That's why I got 94. And then this gives me that address, or excuse me, gives me the value at address 7194. Then I increment I by 1 again to get 2. Data plus 2 really means data plus 2 times the size of an int. So 2 times 4 is 8. That's how I got 98. Gives me that address. So I print 7198, and by dereferencing that address, I get what is at address 7198, which is the 7. So I know this looks strange, and my preference really is to use subscript notation. You never really need to do this, but there's benefits to understanding it. But in terms of how your compiler works, that tool that takes your code and turns it into something the computer understands, it just takes this and turns it into something like this anyway. So the computer really understands this, but I'm so used to reading this is my preference. And then likewise, this statement and this statement really accomplish the same thing. That is, give me an address for some element in the array. So this slide shows us that pointer arithmetic does understand what it's looking at. There's a reason why you need to make a pointer point at the specific type of thing that you're interested in. If I'm pointing at an array of chars, I need a pointer to a char. If I'm pointing at an array of ints, I need an array of ints, because by incrementing by 1, it takes into consideration the size of each object. So here I'm not going to create separate pointers, but I'm just going to use pointer notation to produce a new address. And so since chars take up 1 byte each, whatever address contains the 68 should be 1 less than this address, and 1 less than this address, so forth. And we can see it right here. 68 is stored at address 74. So 97 is stored at the next address, 75. And then 76 contains 114, and 77 contains 105, and so forth. These ints right here take up 4 bytes each. So the first one is stored at address 60. So the next one is 4 bytes away, address 64. The next one is 4 bytes away, address 68. The next one is 4 bytes away, which is 6C. Why is that? Well, these are all hexadecimal numbers. So in hexadecimal, C is equal to the decimal number 12. So 8 plus 4 would be equal to 12, which we just write this way. And then finally, the last number is 4 bytes away from that, which causes my number to roll around to now having a 7 here. But this demonstrates that the pointer arithmetic is making the appropriate jumps to the next object in the array, either an int or a char. Some people like to navigate through an array using a pointer. In some cases, it's computationally beneficial to do that. So here I'm creating a pointer to the 10. So since 10 is an int, this is a pointer to an int, so I write int star p equals d. And so what does this do? Here my I variable is simply a counter to make the loop run 4 times. I don't use it for subscripting. So initially I get down here and p points at the 10, and so when I dereference that address to get what is there, I get the 10, and so this would print 10. And then when I come up here, when I increment I by 1, I also increment p by 1 using pointer arithmetic, which really means updating the address to now point at the 20. So p no longer points at 10. On those previous slides right here, int array never stopped pointing at the 10. I just calculated a new address on every iteration. But int array and char array never stopped pointing at their first elements. Here I am moving the pointer to point to the next element. So now I point at the 20, so when I dereference that, I get the 20. So then I come up and increment p again. So now I'm pointing at the 30, so I can print it. Then I increment p again to point at 40, and I print it. This code right here can actually be replaced by this code, where now I'm combining the dereference operator with the increment operator to both use a value and then increment the pointer afterwards to the next value. These do the same thing. So if you run this, what you'll see is 10, 20, 30, 40, either using this loop or using this loop. What about arrays and functions? When I wanted to use a pointer inside my function to modify a variable outside that function, we said that I would pass the address of the variable, and then on the other end, that is inside the function, I had a pointer that would store that address. So I used the ampersand here, the address operator. But when I'm passing an array, I don't really make a copy of the array. Writing data here automatically gives me the address to the 1. And so I don't need to use the address operator. But what do I write down inside the function? Well, in this case, I have two choices. I can either write int data, assuming that was what I want to call it in my function. I can either write int data square brackets or int star data. It turns out that when I write either one of these, or that is when I write the top one, the compiler is automatically going to treat this as if I've written the bottom one. Now, when I'm passing the address of a specific int, I prefer to use the bottom one. But when I'm passing an array of ints, I prefer to use the top one. And why is that if both of them are really equivalent to the bottom one? It's something else to try to help me remember what my function does. So if you're the person using the function, but yet you're not looking at the actual code, this right here is still a reminder that in order to use this function, the function assumes you're talking about an array of ints. So it at least implies that we're moving through that array in some form. This implies that I'm not doing any such thing. That instead, you're going to give me the address of a single variable, and I'm going to update that single variable. So it's really a conceptual thing, but either way, I can do the same type things, right? But to make clear that even though in this case, when this gets compiled, that writing this basically turns it into this, that does not mean that pointers and arrays are the same thing. In this case, they basically are, but in general, they're not. And let me show you an example of that. So let's say I do this. Int d, 10, 20, 30, 40. And we're going to call this function and give it d. So I'm going to put the entire function here so there's no return type, so it's void, or that is the return type technically because I'm not returning anything. F, and then int, square brackets. And I need to call this something, and we're going to call this x. Okay? And I, for I is equal to 0, I is less than 4, since I know there's 4 elements. I plus plus. So x of I. And I could have called this d, doesn't matter here. Alright, so if I've written that correctly, x initially contains the address of the 10, and then I'm producing these offsets. So it will always technically contain the address of 10. I just produce these offsets to it. So it's x plus 0, x plus 1, x plus 2, x plus 3 is what's going to happen. So I printed the 10, 20, 30, 40. All right? But let's say I do this. Int data, which is an array. And it also contains 4 numbers. 22, 33, 44, 55. And I do this. X equals data. That compiled. And it prints the second array, or prints this array. What happens? Well, I just replaced the address of the 10 that was stored in X with now the address of the 22. So when I say print those 4 numbers beginning at this address, that's what it did. And the reason why is because even though I wrote this, the compiler treats it as that. All right? But let's say I come down here and I create a second array. In fact, we can take this right here. That's fine. All right? But let's say I want to take D here, which if I just do, when I write D right here, I do get the address of the 10. Just like when I wrote X up here, I got the address of the 10. But when I do this, D is equal to data, which is comparable to what I wrote here. I get a compilation error. Assignment to expression with array type. This is not legal because it does not treat this as if I had done this. They're not the same. Are they similar? Sure. Are they related? Sure. Are they exactly the same? No. I just demonstrated that. So no matter how many times somebody's going to tell you that, oh, arrays are just pointers, hopefully this shows you that that's not always the case. And there's actually other situations in which you have to be careful about what you do, right? There are some cases where writing int star x or int x square bracket don't actually work the same, right? So what should you do here? As I said before, my preference is, if I'm going to treat x as containing the address of an array, I prefer to use the square brackets to make it clear that my code expects to be given an array, as opposed to just something like this. Int y equals 4. See, if I'm looking at my code, I go, oh wait, I'm supposed to be given an array, but isn't y just a single int? So maybe I'm not using this correctly. That's the reason behind it. All right? I have more things I want to say about arrays and pointers, but this video is already getting long, so I'm going to create another video. If you find videos like this helpful, please press the subscribe button.